Hello students, here's a question. A large open tank has two holes in the wall. One is a square hole on the side L at the depth Y from the top, and the other is a circular hole of radius R at the depth 4Y from the top. When the tank is completely filled with water, the quantities of water flowing out per second from both the holes are same, and the R is equal to. So in this question, we have to find the value of R, and we know that the rate of flow from both holes from both holes is equal, right? So rate of flow from both holes is equal. So velocity of water at square hole. Velocity at water at square hole is equals to root 2gh. H is replaced with y because depth is equals to y is given in the question, and velocity of water at circular hole is equals to root 2g is multiplied with 4y because depth is 4y, and the rate of flow is equal, so we can write it as as into vs is equals to ac into vc. Now as means area L square, and velocity is root 2gy is equals to area pi r square into root is 2g 4y, and from here we can calculate the value of L square is equals to pi r square into 2, right? And r square is equals to L square divided by 2 pi. From here we can calculate the value of r, which is equals to L divided by root 2 pi. Now check the options. L divided by root 2 pi. The first option is correct. Thank you.
Well, hello students. Now we're going to see this question. The question says that water from tap emerges vertically downwards, okay, with initial speed of 3 meter per second, okay. So the cross-sectional area of the tap is 10 to the power minus 4 meters square. Okay, assume that the pressure is constant throughout the stream of water, okay, and the flow is steady. The cross-sectional area of stream 2 meters below the tap is. So basically we need to find the cross-sectional area below the stream. So basically what will be, basically if you see properly, then you can find the rate of flow. So what will be basically the rate of flow? The rate of flow. So what will be basically the rate of flow? Rate of flow will be rho into g into h. Okay, this h is basically whatever this 2 meters. Okay, so rho will be basically 10 to the power 3 kilogram per meter cube. Okay, so let's name this rate of flow is this basically. So into basically g, which is 10 meter per second square, into height, which is minus 2 meters basically, but let's write it 2 meters. Okay, so what we're going to get from here, we're going to get basically 2 into 10 to the power 4. 2 into, so basically if you see from here, we're going to get 2 into 10 to the power 4. Okay, basically after cutting everything, what we'll get? Kg, only kg, yeah, kg per second. Kg per second. Okay, this is what we're going to get, but let's remove this for now. And also we know the rate of flow. So what you can write basically rate of flow for, if you think about one more equation, it's that rate of flow basically, rate of flow is basically equal to density into V2 minus V1 halved and V2 basically square minus V1 square. So this is basically the rate of flow. This formula is also given in our books. So what we'll write from here, half into, let's write it 10 to the power 3, okay, into V2 square basically we don't know, so we'll just leave it at V square, okay, and V1 square is initial velocity, which is basically 3 meter per second, so it will be basically 9. Okay, so now you can see from equation 1 and equation 2 we can equate it because both are same quantities. So from here what we'll get, half into, let's write equating 1 and 2. Got it? So what we're gonna get from here is basically 2 into 10 to the power 4 will be equal to half into 10 to the power 3 v square minus 9. Okay, this is what we're going to get. So if we take this 2 over here, we'll get 4. So what we're going to get 4, and basically this will cut this, so it will be 40 will be equal to v square minus 9. Okay, this will be our initially. So what we'll get basically, v square will be equal to 49. Okay, from here we'll get v will be equal to 7 meter per second. Okay, so since we got v is equal to 7 meter per second, now we're going to use one last equation, that is the equation of continuity. Okay, equation of continuity. Okay, this is the equation that we are going to use. What is basically the equation of continuity? Equation of continuity is nothing but a1 v1 is equal to a2 v2, where a is area and v is velocity. So what was a1? A1 was basically this 10 to the power minus 4. Okay, and so we are going to write it over here. A1 was basically 10 to the power minus 4, and what was v1? V1 was basically 3. Okay, and basically what was a2? A2 was basically this a2 was what we have to find. Okay, and what was v2? V2 was basically this. V2 is basically this, so it will be 7. Okay, so what we are going to get from here, a2 will be equal to 3 by 7 into 10 to the power minus 4 meters square. Okay, so this is what we're going to get, that a2 is equal to this. Since a2 is equal to this is what we are, our answer is. So if you want to find in points, then you can find 7 divided by 3. Okay, so what you're going to get, you're going to get 0 point, and basically 7 times 3 is 21, but 4 is 28. So 28, which you will get 2, and again you will get 2, so we'll get 14, and basically you have to divide it again and again and again. So this is 66 basically, so you will get a 60 over here. So lastly I'll do this, so you will get 7 times 5, 7 times 7 is 49, and 7 times 8 is basically 56. So you will get 8888. So let's conclude that it will be 4.28 into 10 to the power minus 5 meters square. Okay, so in points also I found the answer, and in fraction also. Okay, so this is basically our final answer. Okay, this will be our answer. Okay, thank you so much.
The given question is, consider a horizontally oriented syringe containing water located at a height of 1.25 meter above the ground. So we are given a syringe uh, arrangement at a height of 1.25 meter from the ground. The diameter of the plunger is 8 mm and the diameter of the nozzle is 2 millimeters. So this piston type structure is called the plunger, whose diameter is given to be 8 mm, and this opening diameter is given to be 2 mm. The plunger is pushed with a constant speed of 0.25 meter per second. Find the horizontal range of water stream on the ground. Take g equals to 10. So we have to find this range. Okay, at what range the water is falling from the nozzle. Okay, so we will have, see, initially we have this diameter of the plunger, and let us calculate the velocity with which the water is coming out from the nozzle. Let this velocity be Vx. So let's find out Vx. let this point be x and let this point be y. So let's apply the principle of continuity at the point x and y. So we know that at x and y both the rate of flow of water would be same, that is a into v, area into velocity must be a constant. So at y position we will have area of y into velocity at y must be equals to area at x into velocity at x, right? So we have to find the velocity at point x, which is equals to area of y divided by area of x multiplied by velocity at point y. So area will be given as area at y will be pi into r square. Okay, and radius will be, see diameter is 4, so radius here will be 4 mm. So we will have here 4 into 10 to the power minus 3 whole square divided by area of the nozzle. We can find as pi r square. Here the diameter is 2 mm, so we will have the radius as 1 mm. So this we will get 1 into 10 to the power minus 3 whole square into the velocity at y is, it is being pushed at a constant speed of 0.25 meter per second, right? So this is 0.25. So we can cancel out the common terms. Pi and pi we can cancel out. 10 to the power minus 3 we can cancel out. And we will get 16 in the numerator multiplied by 0.25. So this will give us the velocity at x is 4 meter per second. Okay, and see this velocity is in horizontal direction. Okay, now see further we have to find this horizontal distance r. Okay, so the time taken by the water to fall from this point and to reach this point will be same as, see water will take same time to cover this vertical distance as well as this horizontal distance, right? So let's first of all calculate the time taken by the water to cover this vertical distance, which is 1.25 meter. So now we will have in the vertical direction, if I apply Newton's second equation of motion, I will get h equals to u y. Okay, the it's in the y direction. Okay, in this direction the velocity into t plus half into, c acceleration at this point will be due to gravity. So this is g t square, where t is the time taken to cover this vertical distance. Now see, the water is coming out of the nozzle is having only x component and its y component is 0, right? So uy will be 0 and we will have h equals to half into 10 into t square, and here h is given to be 1.25. I'll directly place the value 1.25. So from here the value of t square would be equals to this will come out to be 2.5 divided by 10. So this will be 0.25, and if I take square root both the side I will get t equals to 0.5 seconds. That means the water is taking 0.5 seconds to cover this vertical distance. Hence the water will take same time to cover this horizontal distance also. And if I apply the Newton's second equation of motion in the x direction, I will get the range, that is r dash. This must be equal to ux into t plus half into, now see, the acceleration due to gravity is in y direction and there is no acceleration in the x direction, so acceleration will be 0 into t square. So we will simply get r dash equals to ux into t. So this r dash will be equals to ux is this vx only, okay, the x component. So this is 4 multiplied by the time taken is 0.5 seconds. So we will get this horizontal range as 2 meters. So water will cover a horizontal range of 2 meter. This is the required answer. Thank you.
Hello students, today our question is a container of cross-sectional area A resting on a horizontal surface holds two immiscible and incompressible liquid of densities rho and 2 rho as shown in figure. The lower density liquid is open to the atmosphere having pressure P naught. The pressure at the bottom of the container is. So in this question we have to find out the pressure at the bottom at this point. Let's say this point is O. So we have to find out the pressure at O. Now, the atmospheric pressure on the liquid of lower density is P naught. So for this height and for this liquid of density rho, the pressure will be rho into G into H, and for this portion, for this height and for this liquid of density 2 rho, the pressure will be 2 rho G H. So the total pressure net P at O will be, let's say this point is not O, let's say this is A. So PA equal to P naught plus rho GH plus 2 rho GH, rho GH due to this liquid and 2 rho GH due to this liquid. So PA will be P naught plus 3 rho GH. This is our pressure at A. So let's see our options. So option 3, 3 rho GH plus P naught is our correct answer. Thank you.